So today, Monday, February 22nd, I chose a very bad example for case 3. So I want to show you a better one. I think I cut it. It's the first time I edited a YouTube video, tried to cut the last 15 minutes or so off. I hope that's going to work out okay. But if it doesn't, I'll give you some instruction to ignore the last part of it. And on this video, I'm going to show you how to do case 3 on a much more realistic kind of an antiderivative. Okay, so here is the antiderivative we seek. Okay, so we have a linear factor and an irreducible quadratic, which of course is what puts us in case 3, x squared plus 9. Okay, the linear one we treat exactly like we have previously learned. And that is, our goal here is to decompose this function into 2 parts. An unknown constant, which we will solve for over the linear factor, and then a potentially at least a linear factor over the irreducible quadratic. Okay, so this is case 3. It's how we deal with the irreducible. Hopefully, it's obvious that x squared plus 9 is irreducible. So that's our pattern. Now what we're going to do is equate numerators to solve for a, b, and c. So the numerator on the left is 10. And the numerator on the right, if you can imagine, we're going to multiply the first fraction by x squared plus 9 over x squared plus 9. And the second one times x minus 1 over x minus 1. And that will lead to this. So the first thing we do is come up with our decomposition pattern. And then, second thing we do, equate numerators. If you need to do a step between those, if you're not sure you can trust your numerator, just going straight from one to the other, and by all means add, multiply top and bottom by whatever you need, those other denominators. This one is pretty simple, I think, because there's only one linear factor, one quadratic. And so here's where we get. And now we want to solve for the constants. For a, b, and c. The 3 unknowns. I should have said at the beginning, notice there's a 10 in the numerator. I could have, taken that 10 through the integral sign and totally ignored it until the very last stage. But I'm going to leave it in, just, that's the way it is. All right, so because we have a linear factor, there is a good value we can plug in, the value that makes the linear term 0. We need this polynomial to be that polynomial for all values of x. In particular, we need it for x equals 1. Well, on the left-hand side, you always get 10. On the right-hand side, plugging 1 in here wipes out that term. And so we end up with plug 1 in here, we get 1 squared to 1 plus 9, we get 10a. And therefore, a is 1. So if we have a linear factor, we can always nail down one of our constants by plugging in a good value, the value that makes it 0. Okay, that's the only linear factor here. So we're not going to plug in any more values. Instead, I'm going to force this polynomial 10 to be the same as that polynomial. And the only way two polynomials are equal if they have exactly the same powers and coefficients. So I know the value of A. Let's solve for B. So what I'm going to do is I'm going to balance the squares out. I need however many squares I have on the left. I need the same number on the right. Well, I don't have any squares on the left. All I have is a constant. So the coefficient of x squared on the left, it's got to be 0. On the right-hand side, I get an A there. And if you multiply this out, and if you need to multiply it out, but I can see that the only way I can get squares is if I multiply bx against x, which is going to get me a b. Now, I already know that A is 1, so plug that in, and we get that b equals negative. Okay, 2 down, 1 to go. The one we need is C. So C gets involved with x to the first power, and it also gets involved with the constant. C times -1 has no x's involved. Well, it turns out we need to use the constant here. So again, like I said in class, I like to call that case x to the 0. That's just 1, so that's the constant term. On the left-hand side, we have a 10. There is a constant that comes out of the first term, 9a, but a is 1. 9 times 1 is 9. And then I get minus c. Right? B has an x with it, so no constants involve the coefficient b. The only way I can get a constant is right there, -c. And now if I solve that equation, I get c equals negative. So I have all 3 of my constants. And now we'll just plug them back in and get the antiderivative. So the original antiderivative, here it is. I know now I can write as the antiderivative of my decomposition, plugging in the values for A, B, and C. So A is 1, so we have 1 over x minus 1. And then B and C both turned out to be -1. So we get that, just plugging things in. The first antiderivative is just ln, absolute x minus 1. So right at the very end of class, if you were there, I kind of rattled off how to think about this guy right here. What we're going to do, I'll show you in much more detail, have more time. Going to get 2 terms, a log and then an inverse tangent. But here's how it goes. Notice I can factor that minus sign out of both of them, and even through the integral sign, which gets me to x plus 1 minus the integral, x plus 1 over x squared plus 9. Okay, which take the log along for the right. Now break that into 2 antiderivatives. X over x squared plus 9 plus 1 over x squared plus 9. Okay. Now this guy, the derivative of the denominator is 2x. If I throw a 2 in here, and then I cancel it out, so that 2, the cancel out is going to go through the integral sign. Then I have the derivative of the bottom on the top. That's a natural log. I'll say more about that in just a minute. And notice this minus sign is over the whole thing. So let's distribute it across. And then this guy's an inverse tangent. And I think on the very first day of the semester, I showed you what to do if the constant here is not 1. In this case, it's 9. And you remember we take its square root. get 1/3 the inverse tangent of x over 3. Let's see, there's our answer. So this guy, his antiderivative is right there. Maybe not the prettiest function around, but evidently that's what it takes to get a function whose derivative is the thing that we started out with. All right, I promised you I would say one thing about this middle integral, x over x squared plus 9. So technically I'm doing a u substitution. Let u be x squared plus 9 and d. The key to this is to recognize what I said before. I can get the derivative of the bottom. All I'm missing is a constant. The derivative of the bottom is 2x. I have the x. I can't manufacture that x because I can't push the variable through the integral sign, but the constant I can. So that's the key, to recognize whatever is on the bottom, we can get its derivative on the top. So du becomes 2x dx, and therefore a half of a du is x dx. And then we get that 1/2 goes out, we get a u down below, and then x dx is just the u. So you can see why it turns into the. Okay, I apologize for basically wasting 15 minutes of all of our time by picking that terrible example. And I don't think there's anything important about that example that you need to know that we weren't able to illustrate here. Okay? So now you have a better example, and soon, whatever that means, as soon as I can get there, I'll post some problems. Again, I mentioned in class they will not be on the XYZ homework. Rather, I'll post some problems in XYZ, and you'll work on them, and we'll make sure we've got them all figured out before the next exam. All right, thanks. See you Wednesday.